So thus far we have validated our observations that the binomial distribution has a unimodal character. The probabilities increase and then decrease, the point of maximum probability corresponding to a vicinity of n times p. The center of mass of the distribution is exactly n times p, and the probabilities are distributed fairly evenly around that center of mass. Our next question then is, how are the probabilities dispersed around that center of mass? Are they highly dispersed or are they more concentrated? So let's begin by taking a look at a familiar picture. Consider the setting where the number of trials is fixed at 100, and consider the effect of varying the bias probability p. So we have three figures on our picture corresponding to p is equal to 0.3 and p equal to 0.5, a fair coin, and p is equal to 0.8. It's clear visually that the distribution probabilities are most dispersed when the coin is fair, that the probabilities get more concentrated, albeit slightly on this scale, when p moves away from 0.5. A little introspection will convince us that this is entirely reasonable. After all, if one has a fair coin, we have a maximally unpredictable outcome. The moment you put a bias into the coin, the outcome becomes more predictable. And therefore, that should suggest that the probability distribution should be most unpredictable, in other words, should be most spread out or most dispersed when the coin is fair. And of course, we see this in the picture. Now, fixing n has fixed one parameter and we've varied p. The other possibility is to fix the success probability and vary n. So let us suppose that the success probability is fixed at 0.7. Here is a picture corresponding to 10 trials, and we get something very much like what we've seen before. The maximum of this distribution arises exactly at n times p, which is the expected value, and happens at 10 times 0.7 or at 7. If we increase the number of trials while keeping the success probability fixed, say we consider 50 trials, now we've got an experiment where the number of successes can be anything between 0 and 50. The maximum probability outcome corresponds to the setting where we have exactly n times p, or 50 times 0.7, or 35 successes. And now we have a spread around there. If we increase n yet again and look at n is equal to 100 trials, now the largest probability corresponds to the expected value of 100 times 0.7 or 70, the probabilities falling on either side. Now it's very clear when one looks at these pictures that the probabilities appear to be getting increasingly clustered around the center. It'll be convenient to view this in a common scale. After all, when n is 10, then our x-axis is running from 0 through 10. When n is 50, we get from 0 to 50. N is 100, 0 through 100. To put things in a common scale, divide k, the number of successes, by n. Call that x. So as k runs from 0 to n, k over n, or x, runs from 0 to 1. Now we can plot everything on a common scale from 0 to 1 as a function of x. In other words, if you replace k by n times x, then in each of the three cases, we can allow x to run between 0 and 1 and obtain the various binomial curves. Now it's very clear that as n increases, that the probabilities are getting more and more and more concentrated around the central point. Of course, the probability is also decreasing in height, but that is inescapable because as we increase n, there are more and more points with positive mass, and they all have to add to 1 by normalization. But the main idea that there is a shrinking of the support of the distribution, or the effective support of the distribution, seems inescapable. Now, to quantify this, we need to have a clear and simple mathematical way of quantifying this notion of spread around the center. Let us turn to this next. As before, physics and physical intuition gives us a very good starting point for constructing a measure of spread. The picture on your screen shows you a familiar object, a binomial distribution corresponding to 10 tosses of a coin whose success probability is 0.6. More generally, we know what the binomial probabilities look like, and now we also know that the expected value of the distribution occurs exactly at n times p. In this case, with n being 10 and p being 0.6, the expected value coincides exactly at the point 6. Now, suppose one does the experiment. We toss a coin 10 times, and we count the number of successes. Suppose we get 8 successes. Now, it's clear in the picture that the probability of 8 successes is not negligible. It's significant. How far is 8 from the center 6? Well, clearly, 8 minus 6, or 2. Now, it makes little matter whether we are to the right of 6 or to the left of 6. Right. All that matters is how far we are from the center. That gives us an idea of distance from the center. So, a point 4 is just as far from 6 as 8 is on the other side. And therefore, we are more interested in the absolute value of the distance from the center than in the distance itself with a sign. It will be more convenient in such settings to consider the square of the distance. And if we did that, we find an object which is on physical grounds very, very, very familiar. The square of the distance of 0 from 6 is 0 minus 6, the whole squared. Of course, 0 successes occur with a very small probability, b of 0. The square of the distance 1 from 6 is 1 minus 6, the whole squared, or 5 squared. Of course, one success occurs in the setting, again with a very small probability, b of 1. But as k increases, 2, 3, 4, the binomial probability increases, and a spread, k minus the center, the whole squared, becomes not at all unlikely. We simply accumulate the weighted sum of squared distances from the expected value. This is called the variance of the binomial, the variance of the accumulated number of successes, and formally, it's written as 0 minus np the whole squared times the binomial probability at 0 plus 1 minus np the whole squared times the binomial probability at 1. The generic term is if one has k successes, the squared deviation from the center is k minus np the whole squared. You multiply that by b of k, the weight attached to that likelihood, and sum over all possibilities. We have a weighted sum. The student might feel this is vaguely familiar, and indeed it is. In physics, this corresponds exactly to the concept of a moment of inertia of a physical system. And now we have this in hand, we should promptly compact the notation. And putting in place a summation notation says, allow k to run over all possibilities, in this case over all the integers from 0 through n, and for each such value of k, take the squared distance from np, k minus np the whole squared, weight it according to the probability of observing k successes, and add. And now we have a mathematical, precise, clean concept of the idea of spread around the center. This is called a variance, and if we want to identify the underlying experiment, we will write it as VAR for variance of the accumulated number of successes Sn. Tradition compels us, when there are no ambiguous settings, to call this the Greek letter sigma squared. Of course, sigma squared has become part of our common consciousness. It's become part of our common understanding. It's referred to frequently in news. We hear about sigma, 2 sigma deviations, 3 sigma deviations. The concept arises in this idea of a probabilistic moment of inertia. Now, one understands that as we look at the variance, we are looking at a squared deviation, or more precisely, an expected squared deviation from the center of mass. If one wants the spread itself, naturally enough, one should look at the square root of this quantity. This is called the standard deviation. It's of course represented by sigma, and it is defined to be the positive square root of the variance. Of course, given an n and given a p, one can readily compute such a sum. But of course, such a numerical calculation has its own limitations. In particular, it gives us no feeling for the dependence of the spread on the parameters n and p. So, to do this, we're going to need to do some more algebraic spade work. So let's turn to this next. To compute the variance, keep in mind that we have to look at a sum of squared distances, squared deviations from the mean value, from the expectation. To do this, let's go back and take a look at a generic term in the sum. Sigma squared is a sum of k minus np the whole squared weighted by the binomial probabilities. It looks messy, it looks ugly, but to begin with, let's isolate the role of k. Take a look at the whole squared inside the sum. Well, that looks familiar. Well, that is of the form of a minus b the whole squared, which at very early middle school class has taught us is given by the beautiful formula a squared minus 2ab plus b squared. Identify a with k, b with np, and expand out the square. The moment we do that, we've got now an expanded square weighted by binomial probabilities summed over all possibilities. One of the great virtues of addition is that the sum of a bunch of objects can be done in any order whatsoever. This is commonly called the associative property of addition. In this case, let's group the sums together by first grouping a sum over the k squared term, then grouping a sum over the 2np times k term, and then finally grouping the sum over the n squared p squared term. And if we do this, we now have 3 separate sums. It's beginning to look moderately complex, moderately heavy, but it's going to simplify in a hurry. Let's begin by looking at the first sum on the right, the sum of k squared times bn of k. We've already done in our sample exercise a computation of what k squared times bn of k is, as you see, and therefore simply replacing k squared bn of k by our identity involving binomial probabilities of n minus 2 and binomial probabilities of n minus 1 tosses, and summing over all k gives us a moderately complex looking expression, but we immediately realize that the binomial probabilities over bn minus 2 add to 1, the binomial probabilities over bn minus 1 add to 1, and so our entire sum of k squared times bn of kp sums into a very simple expression. We have a closed form answer n times n minus 1 p squared plus n times p. Let's turn to the second sum. Now we have a sum of k times bn of kp, but we have a basic binomial identity. Replace k times bn of kp by a sum involving bn minus 1. The sum of the bn minus 1 probabilities again adds to 1 by normalization, and the entire sum we observe is now just np times 1, or np. Of course, we realize we've just retraced our path in computing the expected value. This sum is exactly the expectation of the accumulated number of successes. And finally, the last sum, and this is the simplest of all. We're summing over all the binomial probabilities corresponding to n tosses of a coin, and that sum manifestly by normalization is 1. Now each of our three terms has been simplified in closed form. Now there's little that remains bar the shouting. All that remains now is assembling algebraically the various expressions and simplifying them. So let's begin. The variance is first a term corresponding to the summation of k squared bn of k, then a term corresponding to the sum of k times bn of k, then finally a term corresponding to the sum of bn of k. And now we've got an expression like this. And a little algebraic massaging sees that the term n squared p squared occurs at several places in the expression. You end up having a total of n squared p squared minus 2n squared p squared plus n squared p squared, and those terms vanish, leaving behind a simpler expression, minus np squared plus n times p. But of course, now we feel irresistibly compelled to simplify it further by factoring out the quantity n times p, leaving behind n times p times 1 minus p. One more step makes it completely transparent. We realize that 1 minus p is exactly the failure probability q, and therefore the variance becomes npq. Again, one could hardly ask for a simpler resolution of what looked like a very complex sum. And so, to summarize, if one has a binomial experiment, if one accumulates successes over n tosses of a coin whose success probability is p, then the expected squared spread around the expected value, around the mean, around the center of mass, in other words, the variance of this distribution is exactly n times p times q. We should very quickly consolidate by taking a look at a picture. So let's go back to the setting where p was 0.7 and we varied n. Now we say that the concentration of the distribution of the spread around the center is now quantitatively clear. Remember, the variance is n times p times q. The standard deviation, or the true measure of the spread, is the square root of the variance and therefore behaves like the square root of n times pq. In other words, if n is 10, then the spread is around square root of n, around plus or minus 2 or 3 around the center. In other words, you start at 7 and you look at plus or minus 2 around 7, and you get most of the mass of the distribution. If n were 50, then the square root of n is about 7, and therefore the spread of the distribution should be around plus or minus 7 units around the center of 35, and again, it's very clear that this is exactly where the spread is. And finally, if n is 100, then the square root of 100 is 10. We expect most of the spread to be within 10 units around the center of 70. The whole point of the exercise is this. As n increases, the spread, the center of mass ineluctably moves to the right. But the relative spread only increases like the square root of n. So if n is 100, then the center is at 70 for a coin with a bias of 0.7. It's at 50 for a coin with bias 0.5. But the spread is about plus or minus 10 in both cases. If n were 10,000, then the spread around the center is only about 100. So yes, of course, the spread is increasing as n increases, but proportionately much, 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 much less than where the center is. We should capture this promptly in a slogan. The binomial distribution is increasingly concentrated around its expected value as n increases.